Assalamualaikum to Sunizam. Today our group consists of me, Mirza, Amir Shami, Amira Sofia and Sofia Anisa will present about the applications of Green theorem. So what is Green's theorem? It connects the line and double integrals into dimension, as well as it converts a calculation from line integral around a closed curve to the double integral over the surrounded by the curve. So how Green's theorem is being invented or inspired? It is inspired by George Green's, a mathematician, in his books, which entitled The Application of Mathematical Analysis to the Theories of Electricity and Magnetism in 1828. So where is the application of Green's theorem? Its applications is in fluid dynamics and electromagnetic or electromagnetism, which is under the mathematical of physics. So today on our case study 1, which is a C curve formed by a parabola and line shown in figure 1. So our vector field is 8y plus exponent x log normal y plus 1 and 5x plus exponent x over y plus 1. So on the left hand side of the vector field is P, which is 8y plus exponent x log normal y plus 1. Then we differentiate P in terms of y. We get 8 plus exponent x over y plus 1. And then for the right hand side of the vector field, which is Q, equals to 4x plus exponent x over y plus 1. And then we differentiate in terms of x, equals to 4 plus exponent x over y plus 1. And then we use double integral r equals dq over dx minus dp over dy. dA equals to the differentiate of q minus differentiate of p. And then we get double integral negative 4 dy dx, which the interval of y from parabola x squared to line 2. And then from x interval from set 2 into set negative 2, from set 2 to set negative 2. And then we do integrate in terms of y first. We get negative 4y, and after that we integrate in terms of x, and then we get the final answer, negative 32 set 2 over 3.
Alright, now for this session, I will explain about the maple coding for the case study 1. First of all, we need to declare the equation of P and Q, which is equation of P is 8y plus exponent of x ln y plus 1, and then Q is 4x plus exponent x over y plus 1. And then we need to differentiate P with respect to y and then differentiate Q with respect to x. And then we need to set the limit for the integral, which is for the limit y, we need to set from x to the power of 2 to 2, and then for the limit x, which is negative square root of 2 until 2. Alright, after that, you need to make the double integration of the limit with negative 4 over dx, and then you will get the answer, which is negative 32 over 3 set 2. And then you need to make the coding from this screen, and then you will get the shape of the equation above.
Next, we continue with our second case study. We also choose a Green's theorem question. The question is, use Green's theorem to evaluate integrate 14x cubed dx plus 2x squared plus y cubed dy, where C is the boundary of the shaded region given in the figure 2 oriented counterclockwise. The first equation is 4 minus x plus 2 squared, and the second one is negative 1 over 2x squared minus 2x. For the manual calculation, the first step is we have to find the p and q. P is 14x cubed and q is 2x squared plus y cubed. Next, we have to differentiate p in terms of y and differentiate q in terms of x. And the result of differentiation of p is 0 and q is 4x. And from this, we can put the results inside the Green's theorem formula, which is double integration dq dx minus dq dy dA. So 4x minus 0, we got 4x. Then we can proceed with the integration. We have to find the limit first. Since we did a double integral of dy dx, the first integration will be in terms of y. So we will use the functions of y from the graph. The limit will be from negative 1 over 2x squared minus 2x to 4 minus x plus 2 squared. The limit for the second integration is from negative 4 to 0, and it is also can be found in the graph given. Then we integrate the 4x in terms of y, and we got 4xy. Since 4 is a constant, we can put it outside of the integration. Then we simplify the equation, and we will get negative 1 over 2x cubed minus 2x squared. We can proceed with the second integration. We integrate in terms of x, and we will get negative x to the power of 4 over 8 minus 2x cubed over 3. After that, we can put the limit, and the final answer is negative 128 over 3.
Hi, my name is Amira, and I'll be explaining about case study 2's maple coding. So on the first line, we can see it's actually the vector p equation, and on the second line is our vector q equation. And on the third line is the upper equation of our shaded area, and on the fourth line is the lower equation of our shaded area. And in order to find our value of x, the limit of x, we need to take 0 and equal it to any equation is possible for this question, any equation as in equation 3 or equation 4. But here I choose equation 3, and then I asked Maple to solve it for me, and I got x equals to negative 4 and x equals to 0, which means the limit for my shaded area is actually from negative 4 until 0. As you can see on the line 7, which is on the right side, is actually I asked Maple to solve it using Green's theorem, and I get negative 1 to 8 over 3. And then I asked Maple to give it to me in decimal form, which I asked it to evaluate it in 7 digits. So I get negative 42.66667. Next, I'll be explaining about how to plot the graph using Maple. So as per you can see my coding here on line 9. So I actually inserted vector p and vector q equation. And then as you can see, R1 is actually my the upper equation of my shaded area. And R2 is actually the lower equation of my shaded area. So I actually changed the variable to t, my x variable to t, and this is the output that I get. And then I asked Maple to plot it based on the coding here, and this is what Maple showed me. Thank you.